of today is Professor Scully, who is going to talk about the black hole entropy from the quantum optical perspective.
Thank you. And thank you, Jim, for setting me up, and Hassim for running this. Great to be here. What I'd like to do today is to, you can turn this on. Hello? Yeah. So what I'd like to do today is tell you about something that I found by mistake. I find it to be intriguing, and in particular, it's the sum and substance of what we're all about at this conference. It's the utilization of our tools, master equations, quantum thermodynamics, applied to an unusual problem, namely the black hole entropy, but applied in an unusual way, and I will explain as I go on. A decade ago, I started working on problems associated with the black hole, but once removed, namely acceleration radiation, the Unruh problem. And you have one there that works better. In particular, I'd like to show you how it is that when a particle accelerates through vacuum, neutral particle, that it radiates, and this radiation comes off in the form of a Planck distribution. This is the so-called Unruh effect. And it ties in quite nicely with what we're doing. As I said, this is something that I worked on a decade ago at Princeton, and more recently, I've been working on the application of these ideas to black hole entropy, thanks to David Lee, our liquid helium expert, and in particular, I've been working in close collaboration with Don Page, who was a student of Hawking's, one of Hawking's early students in the 70s, and Steve Fulling, who is the guy who wrote the book on quantum field theory and curved space-time with Paul Davies. There's another person up here that I didn't put out, Jerry Moore. Probably there's only 2 people in the room who remember Jerry Moore. 3? Okay. Jerry Moore did his thesis on radiation from an accelerating mirror. This is back in the 60s, and was the first guy to ever do these problems. Bryce DeWitt, a famous guy in quantum gravity, then took the problem over, and it's called the Moore-DeWitt solution to the moving mirror problem. So Jerry Moore, a friend, and would be in this list if I had vetted it carefully. But in particular, I'd like to show you how this more or less ties together with the notions of information and neg entropy. Some 20 plus years ago, I became interested in the questions of quantum mechanics and entropy, and in particular, the Maxwell-Demon question, asking in particular, can we use information in a simple way to run an engine without a cooler reservoir? And the answer is yes, and nobody's surprised here. But what was interesting to me was that it was not information, but rather resetting the machine after each cycle that took work. And you never needed to know any thermodynamics to work this problem out, but once you saw how it went, it was this disappearance of information and the so-called eraser along the lines of a guy named Bekenstein, who did the first black hole thinking. He was a student of Wheeler's, and back in what, I guess the early 70s, he came up with the idea that if you were dropping material into a black hole, you were gaining energy as the black hole mass increases, but you are also, in a very real way, losing information. Whatever information you have on this tape recorder goes into the black hole, it's gone forever. This is quite in keeping with the notion that it is not the generation of information that's important in quantum thermodynamics, but the eraser of information. The quintessential eraser is a black hole. Drop it into a black hole and it's gone forever. So this type of logic ties back into the Bekenstein contributions to black hole thermodynamics. And in particular, David Lee and I were working on the question of entropy in the ground state of a Bose condensate. And in particular, if you look at the question of how much energy and how much entropy there would be in a 10 to the 4th atom condensate canonical ensemble, you find that, well, you can use techniques associated with the quantum theory of the laser and indeed calculate the photon statistics, atom statistics. I should ask a question. We call, thanks to Dan Kleppner, we call the Bose condensate an atom laser. You've heard of that. Well, if it's an atom laser, then it should have some photon statistical distribution, right? So what's the atom statistics? I kept saying photon, sorry. What's the atomic statistical distribution? You know, Einstein told us that the average number of particles in the condensate goes like the total number, canonical ensemble, times 1 minus T over Tc to the 3/2 square box. That's the average number. What's the variance in the higher order moments? And in particular, what's the statistics of the atom laser? Well, it turns out to be identical with the statistics found from a laser in which the third order nonlinearities are kept. So this is kind of fun. And in particular then, if you calculate the entropy, as David and I were talking about, of the ground state, you find with this dotted curve the von Neumann entropy, trace rho log rho. And if you go back and do a numerical exact calculation, you get something that fits fairly well. Now, go to the textbooks. In fact, my favorite textbook is by Morse. Morse and Feshbach Morse from MIT. And he says in his wonderful book, the condensed particles are condensed in momentum space, a set of stationary particles having zero energy and zero entropy. But in fact, you do have finite entropy calculated for, say, 10 to the 4 particles. And if you go to 10 to the 24 particles, it's always log of this number. So there it's negligible compared to the entropy associated with the higher temperature contributions, so higher energy states. So I have ground state, first excited state, think parabolic trap. And that's an interesting kind of introduction to these entropy ideas that David and I started working on together. Fast forward to the question of black hole entropy, and in particular, looking at acceleration radiation a la Unruh. This is the way into the game from a quantum optical perspective, and in particular, David Lee asked the question, why should the black hole entropy go like the area of the black hole? So the Schwarzschild radius, 4 pi r squared, is the area, and why should the entropy be related to that? Okay, that was one of his questions. So in working that out, I found that there was some fun to be had in collaboration with Wolfgang and Anatoly Shvydzinski, and later with Don Page and Steve Fullen. Remember, Page is the guy who actually lived with Hawking for several years in Cambridge. So what I'd like to do then is to tell you about black hole thermodynamics in a way that you've probably heard, namely that there's a first law in which the energy, think mass, we set everything equal to 1, 2 pi equals the gravitational constant equals 1. And so the entropy contribution, TDS, is here associated with the area, the rotation, Kerr metric, and the charge on the black hole all contribute to its energy. And that's like what we see in ordinary thermodynamics, first and second law combined. But now go to the question of black hole entropy, or Bekenstein-Hawking entropy, and just remind myself that it is given by the Boltzmann constant, speed of light cubed, divided by the gravitational constant. And what else? Oh yeah, remember that A is 4 pi Schwarzschild radius squared. So keep that in mind. We'll see this, and in fact we'll derive this in a simple way. But in particular, let me go to the question of acceleration radiation first, since I'm pretty sure that most of you haven't followed this particular problem. And Maloney, in his book on the vacuum, says in a very nice article, a uniformly accelerated detector, an atom. We call it detector because they were trying to see what's the temperature of the vacuum in curved space-time. We can go into that later, but think accelerated atom in vacuum, and it looks, if you break the atom open and count the number of atoms in the first excited state, two-level atoms, it looks as if it is at rest in a thermal bath and has a temperature, T sub unru, which is equal to essentially h bar times the acceleration, and Kc is the frequency of the atomic transition. K is the wave vector of the light. Think one mode, first of all. That's good enough. And in Maloney's article, he says that the effect of the acceleration is to promote 0-point fluctuations to a real status. And then he makes the nice statement. It is hardly obvious why this should be the case. It took half a century after the birth of quantum theory, 1925, say, for radiation of this type to be discovered. Now, so with that kind of encouragement and being interested in the question of why that radiation should be thermal, for example, and why it should even exist, I started thinking about the problem along the following lines. Suppose that I have an atom and it is constantly jumping to the excited state, emitting a photon, and then reabsorbing that photon quickly before we violate conservation of energy. And this type of virtual process, we know, goes on and is the basis for the Lamb shift and the Kashmir effect and many other effects. But if we accelerate this atom, it emits a photon and we quickly move the atom, then before it has a chance to reabsorb, it is removed, so to speak. Actually, it's only very slightly removed. And so there's some small probability that the atom will not make the transition back to the ground state, but will instead remain in the excited state, A, and emit a photon. These so-called counter-resonant terms, counter-rotating wave terms, are the essence of the unruh radiation. Please.
Is it the position that the atom changes, or is it that it gets Doppler shifted?
Is it what?
Because if it gets accelerated, it gets Doppler shifted.
Yes. You have to accelerate.
Yeah, but then I thought that the Doppler shift is the more important process than the motion to a different place when accelerate.
You have to be accelerating at a constant rate. If you're accelerating at a rate which is not constant, you've got a harder job, and we'll come to that. But that's an important point. And in fact, when you go to radiation coming from an atom around a black hole, it's not at all clear that these constant acceleration arguments apply. So that's a good point. Well, okay, so this is kind of fun, and I'm going to tell you about it in some detail because I want you to know what the reaction of the general relativity community is. Guys like Fulling and Moore and Don Page, etc., and Unruh, so on. Okay, so the interaction Hamiltonian, as we all know and love it, is just the electric field expressed in terms of an annihilation operator and a creation operator, and I'm traveling down the z-axis. The frequency is nu, and the time t is always measured in cycles of the atom. So the atom is moving. I'm riding along with the atom. By the way, this is all special relativity. For the Unruh problem, it's just special relativity. For the Hawking problem, very different. Then it's strong general relativity. But I can calculate the time in the stationary frame. Here is, say, a cavity, and I'm looking at the time that has elapsed such that if I went through a certain number of cycles, 10 to the 6 cycles, how much time lapsed? And the answer is, it goes like the hyperbolic sine of the acceleration times the time tau. This is easily derived. We're going to use that. And it's this counter-rotating business I mentioned that counts. So now we'll do good first-order perturbation theory. We start with vacuum and the atom in the ground state. We put in this interaction Hamiltonian that we had upstairs in the previous view graph. We want the probability of ending up with one photon of wave vector k, and then we'll sum over all k, perhaps, and the atom in the excited state A. All right, fair enough. So this, then, is expressed immediately in terms of the photon propagator and the atom piece. And notice that they both have positive time here. Normally, you would have a negative sign here for the annihilation of a photon and the creation of an excited state. So now we're going to be inserting this hyperbolic sine and hyperbolic cosine result that you get in a few hours work, or look it up in a book, and do the calculation, and you find that this calculation, as it is presented in that O3 PRL that I referred to, the probability then that you have excited the atom and emitted a photon goes like, first of all, please to note, thank you, Planck. So a 2 pi omega is the atomic frequency times essentially A over C. The C, A divided by C is the acceleration frequency. So the temperature now is coming in, here we see, is proportional to A. And there's prefactors which govern the size of this excitation, going like the coupling constant squared, etc. Now, if you put this in the form of h bar omega, the energy of the atom, divided by a temperature in which K Boltzmann times the temperature appears, you have the Unruh effect. And it's this effect that I was mentioning and is now understood in the context of, say, ordinary parametric oscillator physics. I send in a blue photon and I get out a red and a green photon. In the same way, I'm taking energy from the center of mass. I'm doing some work accelerating this particle. And in particular, then, I produce the atom in an excited state. Think of the atom as a simple harmonic oscillator for the moment. And I produce the field mode in an excited state. So acceleration, radiation, parametric oscillator physics are kind of part and parcel of the same physics. Now, let me jump ahead here just a bit. Yeah. So what we'll do is we'll calculate the density matrix for the radiation in a cavity. Let's think about a cavity, and the cavity is here in free space, and we're shooting atoms through it, perhaps charged and accelerated by some kind of DC field. So we find an equation of motion for the density matrix probability of having n photons, which is just as we saw yesterday and just as we know from the quantum theory of the laser. It's a gain term going like e to the minus xi. Where's xi? It's here. Xi is the short shield radius divided by the speed. Sorry. Let me say just the acceleration. I haven't yet introduced anything to do with black holes. So it's the acceleration over c times omega. Okay, and r is the rate of atomic injection. So this is a gain term. It's like atoms that are hot. And this is an absorption term, like atoms that are cold, just as we teach our students in statistical mechanics. Now, using that result, let's see, using that result, we quickly calculate the density matrix for having n photons in the cavity, which is conveniently written this way as we are familiar with n bar to the nth, where n bar now, please to note, depends only on the frequency of the atom. Doesn't depend on the frequency of light. We're very far detuned from resonance, so the light frequency is not very important. Now, given that equation of motion, we can solve then for the steady state distribution, plug that in here, and in a couple of simple lines end up with an expression for the time rate of change of the entropy. So if I first look at the von Neumann entropy, take the time derivative, all that remains is rho n dot, and I'm going to use that, in particular the equations that appeared on the previous view graph, and I find an expression for the rate of change of entropy in the cavity, okay, going like the average number of photons as it builds up. Now let's go back and start into this business of black hole acceleration. Oh, no, I should go back. How much time have I got, Mr. Chairman? 15 minutes?
15 minutes.
15?
15.
Yeah, good. So I got to tell you, this is kind of fun. Look at the history of this. So we published that 03 paper, and then we got a lot of dissenting mail from people who are relativists and good friends like Asim Barut and Jonathan Dowling. And they say that there is no radiation. That's the first thing you hear. It's all an artifact of the Bogolubov transformations that appear in these calculations. And so we got comments in PhysRev letters that we enjoyed answering and defended ourselves to some effect. Once you're investigated, once somebody disagrees with you, everybody remembers that, but they don't remember what you used to shoot down the argument, right? So we shot down the argument of these guys from the University of Maryland, but still the question was around for a while. And then one time people ask Unruh, hey, what do you think of this? Is there real radiation or not? And Bill Unruh said, it's real enough to cook my steak by. And that's, in fact, the way to think about a lot of this. Namely, it really exists. The radiation in the cavity that we're talking about really exists. And now let's take a step forward and let's come to David Lee's question. David Lee says, hey, can you use this quantum theory of the laser, acceleration, radiation stuff to calculate the entropy of a black hole? And there I have to remind you that what people were doing in the 70s, and the beautiful genius of Hawking, is to look at quantum field theory and curved space-time. But you can understand the physics much more readily this way. Think of a total internal reflection optical system. And that's like the black hole. When light comes up to the horizon, it's reflected. But we know that if I have a glass surface here and I sprinkle dust on it, then some radiation will leak out. And that's the same thing that's going on here, except that the dust is vacuum fluctuation physics. So the perturbation to the Schwarzschild horizon mirror, transmission element, is associated with these vacuum fluctuations. So that the Hawking radiation, properly named because Hawking is the first one to calculate this by quantum field theoretic techniques, the Hawking radiation is radiation from the inside tunneling out. Okay, so remember Schwarzschild, genius, mathematical physicist, was killed in the First World War, and he gave us the line element associated with a spherical gravitational body in which Rg is the Schwarzschild gravitational radius, and pleased to note that it diverges, this metric diverges at r, the distance from the center of the black hole out to our point of observation. And that's something we could talk about if we had time, but our sun, if it were condensed into a black hole, would have a gravitational Schwarzschild radius of 3 kilometers. So let's use these ideas of a horizon as per Schwarzschild, and in particular show that the atoms falling from the outside through the Schwarzschild horizon emit Unruh radiation. It's not really Unruh radiation, but it's something that looks very much like Hawking radiation and is generated by the logic of this Unruh problem that I mentioned. So we find now that I can do the problem. Okay, what problem? Put a cavity here, let the atom fall through that cavity into the black hole, and calculate the entropy change. The entropy change, in this case, is governed by the acceleration of a particle in the vicinity of a black hole, which diverges, please to note, when r equals r Schwarzschild, and goes like the gravitational constant g and the mass of the black hole. The Schwarzschild radius is given here in complete dimensional glory. M is the mass of the black hole, and usually all you see is Rg equals something like 4m. But if I now use this and plug in the fact that as an atom falls into the black hole, it's excited, please remember, by the process of being accelerated, and in that sense there will be a change in the mass of the black hole associated with, in part, the number of photons radiated. The problem deserves more discussion, but let me say it again. As the atom falls through, it gets accelerated. It's now in the excited state. It weighs a little more. It falls into the black hole, and this gives us the ability to relate the change, the parcel of m with respect to t, due to the photons, to the energy per photon at distant observer times n bar dot. Now, the area of a black hole is very simply given by 4 pi Schwarzschild squared. Take that from the previous view graph, and you have such an expression. And now if I take the tram derivative, partial of A, and plug in the acceleration, let's go back, plug in the acceleration expression here, then I've got this result, which is the black hole area theorem in the sense of the Hawking result. Now, Bekenstein had the wit to note that S was somehow related to the area, and Hawking calculated this prefactor, which is in a sense related to the temperature of the emitted radiation. But we didn't use temperature. We used, in fact, a entropy calculation And we're doing a calculation which is different than Hawking in three ways. First of all, we're not inside going out. We're outside falling through a cavity, asking about the properties of the radiation in that cavity and more. Now, I think I've still got 10 minutes, right? More or less?
Less.
Okay. So you might ask, well, okay, maybe you can convince me, but I'm a quantum optics guy, I'm a quantum thermodynamics guy. What do the general relativists say? Well, to begin with, they hate it for several reasons. I mean, this isn't the way they think about these problems. So they have a very powerful machine in which they calculate the Whiteman functions for a vacuum which is in curved space-time. Beautiful calculations, but very different than what we do. Secondly, they say, aha, you can't get acceleration if you're in free fall, right? I maintain I'm in free fall, going right through the cavity into the black hole. They say a particle in free fall has no acceleration, so you're out of luck. So let's put this as a question. Gravitational acceleration of the atoms is a source of confusion. The equivalence principle.
Your cavity is not in free fall.
How big is the cavity?
No, your cavity is not in free fall.
Ha! The cavity is not in free fall. The cavity is fixed on the surface of the star by a rocket, which is holding it there. Yes. Want to be co-author? In particular, the cavity is also very large. Okay, I want this cavity to go from the black hole out several Schwarzschild radii. Now, the equivalence principle, Einstein's equivalence principle, the old elevator story, might seem to say that the freely falling atom is stationary. How can it then be radiating? The answer, the radiation modes are fixed relative to the black hole in the cavity, and indeed relative to the distant stars, and the photons, not the atoms, carry the seed of the acceleration effects. So think of the atom, if you will, from this point of view, as stationary, and the cavity as accelerating by the atom. So let's do that calculation. And in particular now, I have to, once again, same logic, except that now I'm doing honest general relativity. Go to a book like Chandrasekhar, Mathematical Theory of Black Holes, beautiful book. And he will teach you very quickly how to calculate the same quantity we were looking at before, except that whereas for unruh radiation, it's special relativity, and no question about what these times, the trajectory in time and through the spatial coordinate in the cavity, we know what these are. Now it's more complicated, but once you've got the Schwarzschild metric and a little bit of thinking, you can calculate these phase factors. And when you do, you can do the integral, and you get the probability of the photon being left in the cavity. That's what we care about now. We're looking at the radiation. Goes like the same sort of thing we had before, more or less, except that now it's the frequency nu of light that counts. And so the probability for emission from a general relativistic perspective goes more or less like what we had before, except that the frequency of the atom is now replaced by the frequency of the photon. And this is a many-mode problem, so I could have many frequencies, and in that sense, the many-mode structure of the cavity is not a problem either. So in conclusion then, the problem that we were looking at is probably best summarized without putting in this area business, but instead by looking at the time rate of change of the entropy as a quantity which is determined by the Schwarzschild radius and the average emission of photons as we fall through the cavity. So at that point, I'll thank you for your attention. And
questions, comments?
So you have the cavity fixed to the black hole. picture of the general relativists, this is basically, it's not in a free-falling system, so this cavity is accelerated, right?
Yeah.
So does it fill automatically with photons, with UNO radiation, even if there's no atom in there?
No, not from the perspective that I bring to the problem. I'm putting the cavity here and I'm keeping it cold until I start dropping the atoms through. So you could say, well, the walls are made out of atoms, so why don't they radiate? If I have to go that route, I'll take all the walls away and appeal to the distant stars as the vehicle that tells me where I am vis-a-vis the acceleration process. So the answer is no. In my cavity, all the radiation comes from the atoms.
So, Marlan, would you say that this has to do still with the equivalent, with Mach's equivalence principle?
It is a confirmation of Einstein's equivalence principle at a deeper level than people perhaps appreciate it. You remember in the textbooks they teach us that if the elevator is too big and you can see the effects of curvature of the lines, then you don't have equivalence. But here we do have a kind of equivalence. We do find that it doesn't really matter whether the cavity is accelerated or the atoms are accelerated, but the effects of curvature are coming in. So it's a different kind of equivalence.
So would you say that what you have now is fully consistent with general relativity?
It's fully consistent with everything you learn in Chandrasekhar's book, which I recommend, by the way. It's not a book to read, but if you want the answer to your problem, look there. He'll give you every step.
Yeah, I mean, I think it is a bit like the elevator in the sense that I think you do need that the one part of the cavity is accelerating at a slightly different amount than the blossom. So people like Werner Israel have done kind of computations where they look at the cavity which is accelerating, and there somehow it's important that the back wall is accelerating differently to the front wall, and that just allows it to get kind of
So
filled up with radiation.
this is a good point, but let me repeat it because there are several layers to the problem. So the point is, well, the bottom of the cavity and the top of the cavity may be accelerating at different rates, and that's a point. But in my way of looking at things, I don't have any acceleration to the cavity. I'm just fixing it relative to the star, and now I go get my copy of Chandrasekhar and I learn what these nu of tau effects are. So I never address how the cavity might be warped because that's not what I care about. What I care about is what's the trajectory of a photon in time as it interacts with the atom that's actually falling through the cavity. This business of accelerating cavities is not really the way to look at it. It's a stationary cavity. The atom is falling through it, and I'll just go back and solve the equation, solve the wave equation, a la the metric and usual tried and true techniques. But if you don't like that, let me just put in one mirror back to the Jerry Moore DeWitt approach. Okay, one mirror here, and now the light will come down, hit the mirror as it's radiated, and come back. I don't like that because then it's complicated. I got to deal with sine kz instead of e to the I kz. But I can do the problem if we have to. And people have worked on such problems.
Thank you very much.